Hey everybody. Slide clicker. Tom Bessai, Denegri Bessai Studio. We also have our own little fabrication lab in the office. We are running one of these inexpensive desktop printers, and yeah, as Steve suggested, we have lots of problems with that. It takes a lot of dedication to maintain those machines. I also teach at U of T, and increasingly I'm getting involved at Ryerson in various kind of capacities dealing with technology and architecture and teaching. What I want to show you today, and again, I'm going to run through slides like rapid fire because I have way too many, is a project that explains or explores the development of like 3D printed components for lightweight structures, so full-scale components 3D printed. This is very new. It's only just kind of begun. We were collaborating with some engineers on this, and it's very exciting, but it's all very kind of early stages. So I'm going to run you through this project fairly quickly. So overview of the project. So it's a research project, large scale, and it requires a kind of idea of a hybrid. Firstly, printing functional components is starting to become possible, very kind of early stages. Integration as a hybrid structure, I think, is key. So we're doing components, not the whole structure, at one-to-one, rather than thinking about printing a whole building in one go with a big 3D printer, which is what some of the research is looking into. What you get out of this, kind of custom form and performance characteristics. There's a range of 3D printed materials that we were using for this project, all the way from PLA plastic on the kind of weaker end to metal, and I'll show you some examples of each. And above all, there's the notion that you would integrate with other building systems. So this project that I'm showing you was a research project by our practice in collaboration with Cast Connects, as well, who are kind of specialized structural engineers looking at component design, as well as Intuitive, and we were kind of working closely with two of the faculties of architecture in the city, University of Toronto and Ryerson. Their machines are higher-end machines that are serviced and provided by these guys, actually, and in fact, a couple of our components were actually printed at objects for this structure. So, quickly, so there's a picture of the installation. So I got 4 parts to this: concept, design, design development, fabrication, and then finally kind of next steps as far as this type of work. So as far as the concept, the hybridization is between a kind of a bending active structure and 3D printed components. So this is a really good example of a kind of equilibrium bending structure, very lightweight. This thing combines GFRP rods with fabric. For the structure that I'm going to show you, we had to do, of course, material testing on the GFRP, et cetera. As we moved along, we started to do material testing on the combined system between our components that were 3D printed and our bending active components. One of the things that the 3D printing gives you is this kind of dynamic and kind of organic form. So we have quite advanced 3D modeling capacity and simulation capacities in our office and through teaching at the universities. So we're really trying to leverage these tools and these skills to produce outlandish and organic and interesting objects using the technology that 3D printing can allow. These slides show you a couple of the kind of form-finding models for the preliminary structure. Those models are previous to the 3D printed components, but you can start to see where those components are going to kind of occur to hold this structure together. One step back. Can I go back? No. The one that I just passed quickly showed like the process of digitizing or bringing into a computer model the geometry using a microscribe. And then these are some early tests of the geometry and the shape and the look of the 3D printed components. Couple of the nodes. And finally, our kind of registered digital model with all of the 3D printed components designed, and then a kind of, in the foreground, you see a kind of inventory of those elements and start the preparation of those for 3D printing. Okay, so having got through to that stage, we worked through some iterative models to produce the design. So here's those same kind of components. These were the original 3D prints for the 1:6 scale model, so you can see that any one component might be divided into 2 pieces only. That's straight off of a MakerBot. There, those pieces are getting added to the model, and finally, that model kind of completed. So that model isn't just a kind of visualization. It's not a typical architectural model, but rather it is a scaled prototype, the geometry of which exists in the 3D model and is, in fact, the very geometry that will be developed for the final structure. So moving on then in the process, so at this stage we started working with our structural and mechanical engineers in order to look at the division of these components, these nodes, into components and elements that could be fabricated using the 3D print technology that we have available. So Steve could talk to the bed size of a dimension printer, but it's somewhere in the neighborhood of like 12 inches square by a height of maybe 9, 10 inches, something like that. A little larger than the desktop printers. So the component organization is really built off of those dimensions. So you can see one of our Apex nodes is really broken into about 9 parts. So we were working with the engineers to develop shear key connections between those components. Need a lot more work in that regard, but these were the original kind of design in order to allow that the pieces be printed in parts and then added together. This is just a screen capture from Cura, which is the what's the term? The kind of the toolpath program for the Ultimaker desktop printers. Very similar to the software that's run on many of the higher end printers as well. But what you see from the diagrams is how that closed 3D model gets converted into a printing file. So in this instance, we were laying down the component on its side on the bed. So in these printers, it produces a measure of support material to hold up the parts that are kind of floating in space. These guys can speak to that in great detail, like the character of support material, where you want it, how you want to orient your model. All these things become really important issues when developing useful components in 3D printing. This is an Ultimaker printer printing a component vertically. There's another one. You can kind of get a sense. This is an example of a print that has failed. The thing was air printing when we found it after like 10 hours, and it was making this spaghetti on the inside. And this is this is a sectional of a failed print from a dimension machine. So this is more of an institutional quality 3D print. This material is ABS plastic, so it's quite a good structural material. The darker is the support material that gets dissolved away, and then the inside, the section of the component is almost solid, so you have a lot of choices as to how thick you make it. These were some of the structural tests with the shear keys, with the structural engineers. These components have to stand up to bending to the level that the GFRP rods do, so we had some metrics on that. This is kind of a fun shot showing you like what it's like putting all the kind of adhesives together for these components. Top nodes. We had a supplementary system that we added, which was a responsive system of lighting for this project. So the upper nodes had a kind of sensor and LED lighting. We made maybe a bad decision to make these top components, these fairly complex Apex nodes, on the Ultimakers and MakerBots. So we were running prints all across the city. So what we thought the most structurally important nodes we made with dimension printers, institutional quality printers, the kind of $100,000 ones. We made maybe the error of making the top nodes with our desktop printers using PLA plastic. So we had some structural kind of failures on this thing, but what we kind of stupidly decided was that if we want to light them, then this PLA will allow illumination kind of through. So this is some pictures of the install for this thing. This exhibition is on right now, so it's on till the end of August if you wanted to have a look down at King Street at Blue Jays Way. The Design Exchange 3DXL, it's called. That's the final structure at the opening, and just a couple of comments about next steps as far as this work. So first of all, like further structural testing is absolutely key. Secondly, refinement of the component design. Once you know that you have to make divisions in parts, you can start to really kind of make more elaborate and interesting keying designs to put pieces together. Structural modeling, we started in Rhino. These things eventually got developed in SolidWorks, so it is true that you need a certain kind of level of expertise. There is certainly a lot of crossover between these programs, these engineering programs, and BIM software, so that I think could be to everyone's advantage. Scripted or automated design for these parts would be worthwhile, and we're kind of working on that, but it takes a lot of time. And finally, rather than integrating more kind of artistic systems like LED lights, like the idea of all this is that you start to integrate real building systems into amongst components such as these. Finally, this last slide shows one component that we printed from Shapeways in New York in steel. So it was printed as a single steel element. It probably weighs about 5 pounds, and it was done in kind of one go. We were in such a hurry working on this that we haven't really had a chance to test any of the metrics on that part, but our various structural engineers and consultants were very excited to see a kind of a functioning steel component being made, even if it was for a kind of installation. Thank you very much. Sorry it took so long.